Gut, und wir machen weiter mit Dr. Lisa Underberg vom Institut für Automation oder Automation und Kommunikation in Magdeburg. Und Frau Underberg ist uns zugeschaltet, also sie spricht jetzt online. Und ja, ihr Thema ist How do COTS Cellular Non-Public Networks perform? Bitte schön, Sie dürfen loslegen.
Vielen Dank. Hoffe, man hört mich gut. Guten Morgen in die Runde. I switched to English as well, and I will share my presentation in a second, because I think my video is turned off when I start to share slides, so I can wave to you and say goodbye, say hi, later goodbye, say hi from the distance, which is due to a cold I have caught last week, and we're here to spread information and not viruses or bacteria, so thank you for having the last minute opportunity for me to give this talk online in the CMM conference. So that being said, I'm moving to share my presentation with you. And I think that should work now. Maybe I can get a quick feedback from somebody, but otherwise.
We can see your presentation.
Perfect.
Yeah.
Okay, thank you. So I would have loved to be with you in person today, because I would have loved to ask you whether you think that the performance questions for commercial off-the-shelf networks is an easy one to answer. And I would have loved to see what the audience thinks about that question, whether it's easy or hard to answer, because from our experience at IFAK, wireless automation at IFAK, usually people tend to answer that is an easy, simple question. But actually, the deeper you go into that topic, the closer you take a look, it seems or it becomes evident that it's actually a hard question to answer. And in today's talk, I want to highlight some performance testing that we have done, and also highlight the question of where the gap still is and what we need to do to close the gap to really leverage from wireless networks in industrial automation and also in its adjacent fields. And I'd like to start with a little background on the wireless automation team at IFAK. We're here at the confluence point of wireless communication and industrial automation, and we've been there for more than 20 years. Our history at IFAK is wired communication. We're doing a lot of work with Profinet, for example, for 30 years, not 30 years Profinet, but Profibus before. So we have a long history and a lot of experience in the automation side, and also for 20 years on the wireless communication side. I've personally been working with wireless communication systems for industrial automation purposes for more than 10 years already. And since we have a lot of experience in that field, we are also happy to share that. And that's why we decided to lead and also to actively participate several organizations such as GMA or 5G ACIA, where IFAK is a founding member, IEC, DKE. So we're very active in sharing our expertise, and we're not only doing that in the lab, which you can see from some pictures here, we're also doing that in the field. On the right-hand side, you see a QR code that leads you to further information on our measurement system. I will share the QR code with you later as well. Once more, because that is now in the key role, which we've been, the key topic which we've been focusing on, as we need a common language at this confluence point of communication and automation. And now with the next slide, I think I'm going to make Sander very happy, because here it is, the 5G triangle. Yeah, but I think everyone's familiar with that. I think Sander pointed that out very clearly, that there is no such thing as one 5G network. You have to decide which focus you want to set with your network, and then you can have either eMBB or ultra reliable low latency or the massive machine type communication. Or if you don't need either corner, you can go somewhere in the middle, somewhere in between, just as it fits your application. And what we've learned during the last years is, especially in the discussion with 5G, that for many industrial applications, the ultra reliable low latency communication is important, but not as important as the determinism of a communication. So having only low latency doesn't help that much if you have a lot of outliers that are not conformed to that low latency. But Sander pointed that out also, that we have a target here of 99.9% for keeping that. But is that really enough for industrial automation? For example, combining that with a Profinet system. And this is what we are going to find out, or what we are working on in our team with testing cellular networks. And here's just an overview on what we have tested during the last about 18 months with several networks. You see, we also have 4G networks, as 5G wasn't that available off the shelf a couple, maybe more than a year ago. We have tested in total 4 different 5G commercial off-the-shelf networks, 2 4G commercial networks, and 4 different 4G and 5G device types. And selected from that, you see we have, let me take a step back. You see we have a lot of experience with several different network configurations, also having different vendors in the devices and in the network, and we are experienced on how to bring that together. You see some parts on the pictures here as well. We participate in 2 5G ACIA endorsed testbed. One focuses on Profinet and ProfiSafe transmission via 5G. This is the testbed picture you can see here, with the testbed located at the DEMAG Research Factory. We are planning to track the development of different software states of 5G throughout 2 years. So we're conducting performance tests with every major update, and so it's planned to have in 2 years to look back and to see what evolution steps there have been. So you see we have some background, and we know more information than we are going to share today, because today I think it's not helpful to share specific results of specific networks. Instead, I want to raise the awareness for a gap between OT and ICT terminology, and also prioritization. For example, ultra-high low latency is important, but determinism is maybe even more important. Therefore, we anonymized the vendors of both the networks and the devices, just to highlight some, to give you some general feeling on how 4G, 5G performs, on how different devices perform. And with that, I'd like to work towards these 2 guys here, maybe one from the OT side and one from the ICT side. And currently, they are moving towards each other. We want to have a common field, but at the moment, we often see, being at the confluence point, understanding both worlds, that one side maybe wants to buy apples and thinks of apples, and somehow when describing that to the other side thinks I understood, but we're not really talking about apples anymore. So we need a common language for these 2 domains to get together. And this becomes also evident when we look at our results, which we performed with a 4G and a 5G network, which typically have the setup that you can see here. I also think you should see my laser pointer. So moving from left to right in blue, you see typical cellular network components, from a switch, a baseband unit, a base station, and then a 4G or 5G device. And what we did for the following results is we attached a measurement system to the core network side and also to the device side. And we did that with 4 device types. So on this device here, there are 4 different devices. And on the measurement side, we used our FTT, which is a testing system we developed at IFAK, especially for the purpose of industrial automation. And the second is DITG, which I think should be known to a lot of you in the audience, similar as iPerf. It's a software you can install on a PC and do also kind of performance testing with. And yeah, the FTT bases on the measurement device, which we call multiphase, which is a word produced from multiple interfaces, as we are able to support various industrially used interfaces. And for this test we're going to show today, we of course use the Ethernet interface. So when testing this 5G network, today we're focusing on measurements in the downlink. So from this source to this target, we're measuring several performance parameters, and also in the other way around, we're measuring from source to target in the uplink direction. And what exactly we measured were two characteristic parameters, which I want to explain to you so you have a better understanding before we take a look at the results. So you see very small the picture we had on the slide before here on top. Now we have a logical source endpoint, the source on the network side, for example, for the downlink measurement, and we have a target endpoint at the device side as well. So now the source, either the multiphase or the DITG software, generates packets. And in our measurements, we configured a constant transfer interval of 131 milliseconds, which means that at the source interface is supposed to generate one message each 131 milliseconds. And the first parameter we're evaluating is the transmission time. This is the time it takes a message to travel from A to B. And this is something that only the FTT can do because DITG doesn't offer such a synchronization method natively. So we're going to look at FTT results first. To give you a chance to understand the next charts, let's take a closer look at one example chart here. This is the histogram of the transmission time we measured in a 4G network with device type B, using the measurement system FTT, the mentioned transfer interval of 131 milliseconds. And this is a downlink measurement, just as it's depicted here on the left-hand side in the figure. The histogram is scaled on the y-axis logarithmically. So you see that only, okay, so sorry, the x-axis shows the transmission time, so the time it took a message to travel from source to target endpoint. Keeping in mind the logarithmic scale, you see that here with 40 to 50 milliseconds transmission time, there are only really a couple of messages from 100,000 messages that we transmitted. Only really few took that long in this LTE network. I also want to highlight this vertical line. It's noted with P95, which means that 95% of the messages had a transmission time that was faster than this. So left here, this group of messages is 95%. So traveled 95% of the messages traveled with less than 20 milliseconds in this LTE network, which is maybe a little surprising to some people because we usually expect that 5G has a huge impact on the transmission time, and seeing that LTE actually does not perform that bad. We have some outliers, but they are only at 50 milliseconds here. But to see how 5G performed, or an example 5G network performed, let's move to the next slide. You see the same picture on the left-hand side and the right-hand side. Now I will show you the 5G results. But first, I'd like to invite you to think about what you would expect the histogram to look like for a 5G network from what you've heard about 5G. Where is the P95 value? Does it also have multiple groups of messages, or does it have only one group of messages? What's the maximum transmission time that we measured? And this is also why I would have loved to be with you in person. But anyhow, let's make the best of it. I hope you have a an image in your mind, and this is now, we can compare it now to our measurement results. We see the P95 value being at about 7 milliseconds, which means a lot of the messages travel faster than 7 milliseconds. But we also see some outliers having more than 10 milliseconds. And from the network that we looked at, I think it's more than what the original goal of ultra reliable would be. So there is some way to go, but we're only talking about a release 15 network. So it is clear that 5G networks will improve. And you see, of course, there is a clear improvement compared to 4G as well. So having a safety critical communication link with a transfer interval of 50 or 20 milliseconds should be no problem to keep that communication running, or the system running, not moving into a safety stop. These are downlink values. The LTE system was configured with a ratio of 1:1. The 5G system is configured with a ratio of 1:4, so meaning downlink has more resources allocated than the uplink has. Of course, these measurements are not even close to the capacity limit of both networks. But still, we see some impact on the uplink, because the uplink histograms clearly are different. And now I'd again like to invite you to picture in your mind how these histograms might look like. For 4G, I'm going to share with you right now. We see here as well, there are some outliers up to 50 milliseconds, but the majority is again closer to 20 milliseconds or less than 30 milliseconds, with the P95 being at approximately 26 milliseconds here. For 5G, it looks different and maybe unexpectedly longer. We saw in the uplink that we could have most messages with a transmission time of less than 10 milliseconds. Here, it's up to 28 milliseconds for the P95 histogram. So we used for both measurements the same device type. So we really should see the impact of the network here in this comparison. Now you might think, okay, it's one device type. I already said we measured several device types. And now in the next step, I want to compare two device types, meaning device type B, which we see now on the left-hand side, similar to the slide before. And now device type C will be compared. Maybe one side note, I think most of you are familiar that there are basically two industrial 5G routers on the market, and these two. B and C are the two 5G industrial routers that are commercially available, and we use the commercially available setting. And then we now have the same test setup as with the device type B. We just switched the device, and yeah, again, maybe some of you have already an idea how it looks like, or what the difference will be, or will it be the same? And will it be the same? Yes and no. The distribution we saw with the second device type is basically the same, but it was a lot faster than device type B. So meaning you should not only look at the network, you also have to look at the implementations that you receive at your device side. That being said, I'd like to move on to the next set of results, which is results on the update time. You see again on the left-hand side the familiar picture with the transfer interval and the transmission time. Now in industrial applications, often not only the transmission time is relevant, but also the update time, which is somehow the inter-arrival time between two consecutive messages. And if the network is really deterministic and does only what we want it to do, then the update time should be identical to the transfer interval. But unluckily, of course, networks usually have some processing. You have to wait for allocated resources, which leads to a histogram of the update time being centered at the transfer interval of 131 milliseconds. The time is on the x-axis here. But we have some deviations. Some messages travel, they do not travel faster, sorry. They arrive shorter to each other, and others have a larger distance time-wise, but still centered at 131 milliseconds. Now you have to be aware of your application, whether the network will suit your application or not. But let's get to that in a second. This is a 4G result with device type B again. And if we now compare it to a 5G result, you can also in your mind think whether how that would look. And if you remember how the transmission time histogram looked, you might not be that surprised with the result, which is a smaller histogram. We have a smaller deviation in the transmission time, which leads to a more homogeneous update time measurement as well. So now this is a good point for us to take a look into the second measurement system that we used. On the left-hand side, you see the FTT. We measured here with the measurement system we developed at IFAK. Now we're using device type A, which is an evaluation kit, and DITG. So two things changed in our measurements. And here we see with the same network, different device type, different measurement system, the histogram gets a lot broader. And then you're looking at device type B with DITG. So similar to the first histogram, except for the measurement system, we see that also it was not the device, it was the measurement system causing, or most likely the measurement system causing the larger variation in the update time. Let's take a look why that is. Again, the familiar picture, you have a transfer interval that is configured to 131 milliseconds, and with the FTT, we can achieve that with an accuracy of ±1 microsecond. It is an FPGA-based implementation, so in hardware, nothing should really happen here, and we also have a very good synchronization. That's different with DITG. DITG is subjected to an operating system. And looking at the output of the transfer intervals that DITG gives you as a user, you see that we easily have a ±10 millisecond deviation only in generating the messages. So we could have different transmission times in the networks. That's what I indicated here with different arrow angles. But most crucial is that the generation here deviates much. So while the mean value of 131 millisecond is kept, the generation is not equidistant, which leads to a larger histogram. So what do we learn from that? I think we definitely learn that in the end, our application determines which communication system with which measurement system is suitable. So if you have an industrial automation application that has very strict time reliability, time determinism requirements, you should not measure with DITG because your measurement system will have an impact on what you measure that is a magnitude too big for your actual application. If you think maybe of an augmented reality use case, or maybe even the robot we heard in the first talk today for bar services, that might not be necessary. So you really have to think, what is your application and how do I find a suitable communication and how do I verify that this communication system I chose is the right measurement system? So using the last minutes, I want to just give you a quick indication where you can find some further reading on application and performance profiling, because from our perspective at IFAK, this is key to a common language to describe application and the performance of a network with the same words, with the same definitions of parameters. And you can easily do that with quantitative requirements at least. So having a requirement profile that you can show in a spiderweb diagram, I think that's not too unfamiliar with most of you. And if you now have a common language, you can not only put the requirement profile in there, but also the performance profile of different technologies. For example, technology A or technology B, and then you have an indication on which decision you might want to take. Of course, you also have to take into account qualitative requirements as well when you make your decision. So not only the performance has to be well enough, but also some qualitative requirements have to be fulfilled. For further reading, I recommend you to take a look in the VDE guideline 2185, part 1. There you can find some definitions as well and some guideline for non-wireless experts, how to approach an application profiling. One more crucial topic is that we do not only need to describe the characteristic parameters here, meaning the data rate or the transmission time a network provides. We also need always to put that into context with the influencing quantities. Does the transmission time refer to an empty network, or does it refer to a network that is close to its capacity limits? How was the transfer behavior? How many other devices were there? We really need both sides here. So a comprehensive set of parameters has to consist of both parties, the influencing quantities to show what are the conditions for the characteristic or performance parameters that I measured or that I'm using. And this set of parameters is not only used to describe requirements, but also to describe an assured performance or a current status of an industrial communication system. Now, especially looking at the current status, we also need to take a look into how to measure that. And that's where we propose to have a clear division between a testing system and a system under test, as we have conducted in our results that I've shared with you a couple of minutes ago. And if you're interested here in further reading, I can recommend 2 5G ACIA white papers where IFAK, of course, has been contributing, and the part 4 of the before mentioned guideline. So now coming to an end, I'd like to conclude that we need an agreed methodological approach for performance testing to have comparable results. Not only comparable results, but also to allow people from different backgrounds to communicate clearly on the same thing. So what I wish for in the future is that we focus on communication, but not only for machines, also for people, so we learn how to talk about the same thing. Here again, you see the QR code for our measurement system if you're interested, but also, since I could not be there in person, a colleague is there, Gustavo Cainelli. Maybe Gustavo can wave friendly to the people around you, because after my talk or even in the lunch break, please get in touch with Gustavo about the measurements. He will have the slides ready to discuss with you if you're interested. And also he's very familiar with our measurement system. In case you're following remotely, you can get in touch with me because I have basically a last-minute free day, and I could offer to spend the lunch break with you virtually and discuss some parts of this presentation. And with that, I'd like to conclude. Thank you very much for your kind attention, and looking forward to talking to you.
Okay, great. Thank you. Thank you very much, Frau Underberg, and that you made it possible to speak to us, although you couldn't get here. Are there any questions? So I have one. You mentioned the gap between the OT and the ICT in terms of terminology. Oh my God. And other topics. Do you see this integration of OT and IT or ICT as one main challenge for the adoption of 5G or for the adoption of this whole smart manufacturing?
Yes, I think it is key that we learn to speak a common language, that we learn to develop application profiles and performance profiles that we can actually compare how networks perform and what an application requires. However, I'd like to restrict that a little because for applications that do not have that strict requirements or that do not intend to use a system close to its capacity limit, it might not be necessary to dig too deep. But for challenging applications, especially from industrial automation, that might be the case. We really need that to enable networks being used in these applications.
I think it was very important to say that companies mustn't underestimate that topic, this whole integration between IT and OT, I think. Yeah. Okay.
Also, what we experienced when integrating these 4 device types in 5 or 7 different networks, it was not yet plug and play. But this is why we recommend to get in touch with the technology right now, early on. And as you saw from the results, you can use today's commercially available networks already for a lot of use cases.
Okay, so well, thank you again for your presentation, for your lecture. And as you said, your colleague is here, and he can ask all the questions that here the participants have. And you also think you said you are available during the lunchtime. For remote participants, great.
Just drop me an email.
Great, cool. Okay, thank you very much.
Okay, thank you everyone. Have a nice day at CMM.
Thanks, bye.